Hey folks, I'm Trek. Let's learn calculus. Alright folks, let's get started. To begin us off, let's talk about what calculus really is. At its heart, calculus is the study of how functions change. Now that might not make sense to you just yet, so let's first talk about motion. If you look over here, I have here a graph of what I'm going to call a car. It doesn't move necessarily exactly like a car would, but let's pretend this line here is a car. The dot is where the front tires are, and the tail is where the back tires are. This car is traveling in an XY plane. It's kind of doing a little serpentine action here. But a pre-calculus sort of question would be, where is the car at time t? At 10 seconds in, where is the car? Whereas a calculus sort of question would be, how fast is the car turning at time t? At 5 seconds in, how fast is it turning? And it's important to understand that the speed at which the car turns is neither an input to the problem, nor is it an output. I mean, if we have a position function, this is going to take a time, and it's going to output a position. The speed at which it changes is neither. It is neither of those things. It is instead an analysis of the function itself. And these are the sorts of things that calculus concerns itself with. Whereas prior to now, you've always had a goal of evaluating some sort of question or problem. Now we're going to talk a lot about how things are changing, how they're evolving, and what we can derive and model based on that. The first topic in calculus is what we call the derivative. And simply put, a derivative is a function which describes changes in another function. And you already have seen quite a few examples of this. Let me give you one that you've almost certainly seen. Alright, so I've written down two of the basic kinematic equations you learn in physics. The first one is the position function. It tells you the location of an object in if you have its time and acceleration and initial velocity. Velocity describes a rate of change in position and is thusly its derivative. The derivative of position is velocity. Likewise, acceleration, which in our case, in the case of the kinematic equations, is just a constant, it describes change in velocity with regards to time, and it is therefore its derivative. You see what we're doing here? Each of these functions in turn describes the function above it. And this is what we're looking for when we talk about a derivative. Okay, so how do we find the derivative is our first question. Well, in the past, you have likely been familiarized with an approach called rise over run. Rise over run, just to refresh your memory, is pretty simple. All you do is you take 2 points. We'll call this one P2, and we'll use this one right here. You can pick any point, really. P2 and P1. And you subtract P2y minus P1y, and you divide that by P2x minus P1x. And this gives you a slope, or a rise over run. In this case, we get 7 minus 5 over 6 minus 4, which comes out to be 2 over 2, or 1. So we go up 2 over 2, and that gives us a slope of 1. Rise over 1 works well for linear functions like f of x equals x, like we just worked with. But it doesn't work when you move on to higher order polynomials like f of x equals x squared. And that's because it doesn't properly follow the curve. Like, for example, if we try the process, the rise over run process from these 2 points, do one line there, a line here. And let's just estimate these for the moment, 3.5 and 1.5. What we're actually estimating isn't the slope of this curve, because it clearly changes. I mean, right here it seems to be like, something like that, but up here it's much steeper. And that's because what rise over run actually tells you is the average rate of change. Let me bring up a line here. Don't worry about this, it's just controlling the graphics here. But as you can see, what we're actually estimating is the slope of this blue line here, which is different from the actual curve slope at several points, at most of it actually. So if our goal is to come up with a function that tells us the exact rate of change of our function f of x equals x squared, how might we get closer to the answer? This one, if rise over run tells us the average rate of change, how might we find the instantaneous rate of change, as in the rate of change at any single point along the curve? Well, what we're going to do is we're going to decrease the interval. This 1.5 here, our run of rise over run, if we decrease that, we actually get a more accurate estimation of the slope. I'm going to call our run of rise over run h, and that's just so that I can do something like this. I can call this p2. Instead of calling it p2, I can call it x comma, I can call our 2 points f of x, x comma f of x, and x plus h comma f of x plus h. Those would be the 2 points we compare when we do our rise over run. And this way we can control our interval just by decreasing h. So let's clear this out, and let's get rid of that too. And right now we have an interval of h equals 1.5. Let's try decreasing it to 1. As you can see, our interval changed. Instead of going from 0.5 to 2, we're going from 0.5 to 1.5. And if we do rise over run again, exact same as before, you can see that our blue line, which is what we're actually calculating, is much closer to the curve. And let's decrease h again to 0.5, and then 0.25. I'm not going to go into, I'm not going to draw more rise over runs, but you should be able to see that the smaller we get with h, the more and more close our blue line is to our black line. And we can use rise over run to tell us the slope of the blue line, so if we can make the blue line exactly the same as the black line, then we have a rate of change for our function. But right now we don't have the language to describe what happens as h gets close to 0. For that we must learn about limits, which we'll have to do another day. Hey, I just really want to thank you all for watching. Hopefully you're learning a lot. I'm going to try to take this slow and cover all the concepts so that you can really sort of build a base work for going deeper and deeper into calculus. I do want to give shout-outs to the people on my side here. First, you got Math BFF, who does math videos herself, and they are amazing. In fact, they were kind of part of the inspiration for improving my editing. Also, GDQ marathon. It's a charity marathon where some of the most talented video game people and personalities in the world get together and speedrun video games for charity. Check that out and support them if you can. Besides that, I guess I'll see you all next time.